So now we have the second talk by Anurag Banerjee. He's going to talk about density wave states in the strongly correlated Hubbard model.
Okay, so good morning. So I'll talk about density wave states in the strongly correlated Hubbard model. And this is a doped Hubbard model where it is expected like the kind of quantum Monte Carlo algorithms will not work because of the sign problem. So there are different approximation schemes that you can do here in order to guess an answer which might or might not be correct. So I'll propose a formalism which was proposed first by Hubbard in 1965. And from there, we did a real space calculation for that to get translation symmetry breaking, like charge density wave states in the strongly correlated Hubbard model. And these are the collaborators. I've worked with Emil and Catherine and Chiranjit and Amit from IISA Kolkata in India. So for the references, I'd say like this is so this is the reference for the formalism, and there is another phenomenology that you can look at with this formalism is this orbital selective phase where a preprint is available. And this one is the preprint will be available soon, and you can look at it. So let us look at what we are talking about. We are looking at so density wave states in the Hubbard model, particularly in a doped Hubbard model. So here the density is fixed at 0.875. Here, what we know, what we want to work with is like the strong correlation regime of the Hubbard model, such that your U is much larger than your hopping strength T. So for that, few of the results are very well known. For example, in the sorry, not very well known, but there are some disagreements. But it is known that it has stripes, some kind of stripes in the as a solution of this kind of in this doping. So what we see here on the left is some VMC calculations. The dots are showing what is the hole doping at that point. And you see like some points, the hole doping goes almost to 0. That means it becomes half filled. And at that point, there is an antiferromagnetism. This is also reproduced in another VMC calculation, independent VMC calculation here, where you see that there are stripes and you get almost a half filled regions of stripes. And in those half filled regions, since antiferromagnetism is stabilized, you should see some local stripes of antiferromagnetism. Next, there are some other calculations which you can do in n-leg ladder DMRG. This is on 32x6 system with periodic boundary conditions. So this method stabilizes different wavelengths. So here the wavelength was 8. I didn't mention, but you can also stabilize other wavelengths like 4, 5, 6, others. So these are for two different wavelengths that you see here. This is at 8 and this is at 5.3. But you can see the difference between the VMC and this is like, this is not going to 1. I mean, this is not half filled. This is not forming half filled stripes as we see in the VMC calculations. So there was a multi-method calculation which was being performed at this doping. And it was observed that many different stripes, like from the wavelength of 4 to wavelength of 10, it seems to have same kind of energy difference between them. So the question now is like, how can we think about the stripes? What is the mechanism of the formation of these stripes? And can we get another method from which we can extract such physics? Okay. This lambda? So the lambda is the wavelength of the charge density wave solution that you can stabilize using the DMRG calculation. Doping is always the same in all these. So this is for so all these solutions are for the same set of parameter of Hubbard, like U and N. Okay.
The open question is, what kind of charge density wave is stabilized? Is that what we are after, or?
No, I'm saying like, is there a half filled stripes which are being formed for example, like in VMC, as you found like this one,
yeah,
and formation of antiferromagnetism. Although you see antiferromagnetism here, it's not going to half filling. I mean,
okay,
there's a question there.
How did they get the data for VMC? Isn't there a sign problem as well? Because
Yeah, I think there is. I don't know, but I think they do constraint path. I don't know. I mean, it's I've not looked into it in details, but
No, so there's no sign problem. I don't know this one paper, but there's no sign problem for that. Well, for the VMC.
no. For here there is an AFQMC, but
Yeah, but that's constraint path. That's UAs. I
Yeah.
think.
yeah,
I'm
this
not
is
sure.
constraint path. I
This
think.
constraint path. I do a question. I'm still confused. You have the same parameters and you have two solutions.
There are not two, but there are 10.
And so they're close in energy, or
They are close in energy.
I'm sorry. I'm asking many stupid questions. I said, but so all these. So where do I see the energy here?
So this one is the energy. So this is the difference of energy from the lowest
Okay.
energy solution. Like which one is 8 for them? This is the 8, and this is the dotted line of 8. And then they compare with 8 other length stripes. Like this one is for 4, this one is for 5.
Okay.
And so they find. So it depends on the initial trial
Sure,
that
of course,
in the
right.
DMRG that you stabilize different
Right.
length. So that's it's kind of
Thank
like
you. Yeah, sure.
it seems like a self-consistent calculations here. So now I will try to reproduce this physics using another method, or get another answer for this kind of questions that are being asked for stripes around this doping. Also, I will try to study what happens when we change the doping in both directions and what kind of physics we can capture. So now, so the formalism I'm working is like the composite Hubbard operator formalism. So this is the Hubbard model. This is the Hubbard model with the kinetic energy term and the on-site repulsion. So if I work in the atomic limit that is at t equal to 0, I can write my electron annihilation operator as a sum of 2 operators, and these are given by excitations. These are eta and xi. These etas are the holons, and this will primarily form the lower Hubbard band of our model. And there are doublons, and this is given by this, and this will be the upper Hubbard band primarily of this. But in atomic limit, yes, this is the upper Hubbard band of the system. So eta and xi are defined here, right? I mean, this is an holon. We call it holon, and we call it doublon. I mean, you can see like this. This will create a double occupancy, and this will create a hole. So we start with a state where everything is singly occupied, like a Mott state, and then we assume this kind of excitations on top of that. So now I will just outline the formalism, what Hubbard did back in 1965, but just in real space. What I will do, I will write my basis, and this is my composite operator basis with xi and eta. And then with all the sites labeled from 1 to n, you can also take care of the spin, but we will work with the paramagnetic assumption that is that all the spin up and spin down are the same. Next, we can define the imaginary time Green's function for the composite operators like this. And then we can do the equation of motion. And then once you apply the equation of motion formalism, you'll get one. The derivative one will be like a delta function at equal time. If for a normal fermionic commutation, this should be an identity delta ij. But here it's not. It's you have to calculate the xi eta and eta eta correlations, and you have to find a matrix which will be given by I, which is called the normalization matrix, and then you will get this quantity. But now we run into difficulties. If you are working on atomic limit, the eta and xi will always get currents, which is this j of tau, which is always along our composite operator basis, which has been defined. But as soon as you have a hopping, this will generate other terms, the current will not be in the direction of the defined basis here. So your basis will increase, and then you will run into difficulty. So to close the equation, what we do, we assume that the current is always along the atomic limit basis that we have defined, and we throw away all the terms that are coming because of hopping. So this is not from the hopping, but we consider hopping which are along the current, along the bases that we have defined, but we throw away the terms which generates hopping to other operators. So this, in principle, allows you to close this equation now, and then you can take it to this side, do a Fourier transform, go to Matsubara frequencies, and then do an analytical continuation and get the composite retarded or advanced Green's functions. There is a question, I think.
Algebra of the Xi's are different, of course.
Yeah, we have to calculate. So that's why you will get these matrices which are not, which are not the same. I think this will not be an identity matrix. So you have to, one has to calculate these matrices again, because this will not follow the same commutation relations of C and C daggers. We have to use the commutation relation. We have to calculate the algebra from, I mean, yeah. So what, yeah, it will be from fermions. I mean, so the formalism starts from here. Like we want to calculate, let's say we want to calculate the Green's function for the fermions. And this we have, you can show like this is the sum of eta and xi, and then it will like break apart. Like, so it will be Fermi functions that will come in this kind of calculation. Yeah.
This is not a unitary transformation which takes the C's to your new fermions, or are these fermions even? Or?
No, these are not exactly fermions, but these are close to fermions. These are
In some controlled way, or?
I don't think so. I mean, it's eta and xi. You will. It's not a fermionic commutation relation, at least. Okay. So it is just.
So what is this? How do you recast these problems in terms of these new variables which are not fermions? What does it mean that you're calculating Green's functions and doing things for?
No, but so the goal is to calculate the Matsubara Green's function, let's say, for the fermions.
Yeah.
And then from this relation that you wrote, this is not unique, like this choice is not unique.
Yeah.
But this is our guess, like this doublon and holon. And then you can write down, this is a sum of eta part and xi part.
Yeah.
So then it follows, like, then you can also say that the equation of motion will also follow the same procedure. That's what I'm saying.
I see. So it's an operator anyway, and so you can write down the equations of motion.
Equation of motion for the fermions, and then continue using the composite operators.
Okay. Thank you.
So okay, so in everything that we did here, we didn't do the whole formalism, but what will happen is, like, when we calculate the expectation values, we'll get some kind of self-consistent parameters. One of them is very simple. It is the density. The density is just the sum over the C dagger ICI over the sigmas. We don't care about spin at the moment. We assume that the spin of two up and down is the same. But one can perform this for not assuming this paramagnetic assumption also. Then we have this kind of another operator, but these are single particle operators. So xi dagger xi, this we can calculate within our formalism. But then we run into another difficulty, which is this p term, which is actually a nearest neighbor. This looks like a 2-point correlation in INJ, S minus Sj, and then this delta is actually like on-site pairing delta C dagger or CC. So this kind of things. So now, in order to close this equation, one needs this kind of 2-point correlation function, which we cannot get from a single particle Green's function that we have defined before. So one can do Weeks decomposition here and get away with it. But Roth also, there is a paper by Roth back in 1969 where he suggested the same formalism in order to calculate this kind of P's. But one can also, in general, get it from a Weeks decomposition or other things. So now I will just summarize what are the approximations that we are using. We are using strong correlations, which are being treated within this kind of composite operator method. So hoppings are treated as perturbations. Hubbard operators are doublons and holons. There are other 16 Hubbard operators which we ignore. Only orders that we can consider now is the charge order, and no magnetic ordering or superconducting ordering for now. What we are working next, this is another assumption on top of that, is a unidirectional density wave. So the density wave will be uniform along one direction, so that we can do a Fourier transform go to momentum space in one direction and perform the calculation in a large system size. So the procedure is like, we will initialize the trial density of this unidirectional charge density wave from a wavelength of 30 to a wavelength of 60 lattice spacing, because we can do up to 120 lattice sites. And then we study the self-consistent density wave order, if any. And these are the parameters that I'm looking at. I've also worked with u equal to 12. And the doping will be from doping, which is defined as delta here, which is 1 over minus the average density, will be from 0.06 to 0.2. So now I will flash the results that we get from the self-consistent. So we get multiple density wave profiles for this. This is the this is for the 1/4. That means the wavelength is 4. So what we see, like, there is a formation of a Mott region where the density is exactly 1. And then there is some hole rich regions that you see here. So here the doping is 0.1. So the density is average density is 0.90. And then there is a strong oscillation, as you see, like a square wave kind of a structure that you get. So if you do a Fourier transform of this, and this is only from this 0 to 0.5 in this kind of units, you see like that the peak is at expected 0.25, and there is a strong peak. So this is my dominant peak. I will call this the dominant peak after the self-consistency, and this is where, so this is 0.25. And then what I will do, I will compare different solutions that I get from this kind of procedure. And this is where it lies. This is my energy difference compared with the, so I will show this again, but let's look at this. This one is here. This is how you identify. So this is the energy as a function of different QNs that we show here. Next, we can get also at the same parameters. This is delta is equal to 0.1. You get for 5. There are some, so then there the hole rich regions has become larger. There is still a formation of Mott regions that we see. We see 2 peaks in the Fourier transform. And so, but the dominant one is the expected one. So then we just pick this in this, when we plot this one, we use this one as the number. So this is the 0.2, and this is here. You see that's orange one. But as I said, we'll try up to the very large wavelength, and this is what I get for 60. And this is, as you see, like there is a very large Mott region that we are forming, and then we have also a peak at a very small wave vector. And this is below the uniform line that you can see here. So now what I'm trying, what I will show you is how this energy difference goes as a function of doping. So the first one is at 0.075. We see like this is the uniform line, and then there are many solutions which are below this uniform line. There are states which are above this line, but the solutions which are below the line are very large wavelength solutions. So for example, of the order of 10, 20, and 60. As we increase doping, the things which are below the lines, first of all, it goes, okay. Yeah,
Are these stable solutions?
yeah,
Or-
what do you mean by stable?
I mean, I guess you could have some phase separation, right? I mean, so you have to, you can get, you know, if I think if you do a Maxwell construction, you can see if you look at the chemical, the energy, I mean, the chemical potential versus doping, for example, the N versus mu, if is that a consistent, I think, you know, it has to have a given sign.
Yeah.
D of N over D mu has to be positive, right?
Yeah.
Is that satisfied by your solutions? I mean, because if it's not, that means that you have phase separation.
Yeah, I mean, for example, if you, so the only solution which we can track as a function of N as a function of mu is the uniform one. The one which which will have 0 wavelength basically. So this one, and this one doesn't show any kind of signatures of phase separation as of now. But when we do it in real space, it seems to it seems like if you this is kind of a phase separation of holes. Yeah. 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 So okay. So this. Yeah. So then, what happens at higher doping at this doping level? We see that we start losing solutions which are basically of the wavelength of 4 or 5. So there is nothing here, and we get some long wavelength solutions which are there. And finally, at doping point 2, we don't stabilize even any self-consistent modulated Mott regions anymore. So with this, what we can say, okay, so what we can say about the physical quantities where this will be visible. So first of all, what I plot is a low energy density of state. So this is the lower Hubbard band. This is the end of the lower Hubbard band. And this is my density of state. And you see there are multiple peaks, very complicated structure that we see here. But can we understand what are these? So let's say at Fermi, first of all, at Fermi energy for this kind of charge density wave that we showed, there is no gap. It seems there is no gap. So yeah. But there is also a strong peak at the negative energies, which I marked at E2. And then this one is low energy is E1 and then E3. Next, what I will do, I will plot the spatial profile of the local density of state at these energies. And what we see that the low energy excitations, I went away. So the low energy excitations are always at the hole rich regions. So wherever the regions have holes, this has a strong peak. And wherever this is Mott, this is going down. This is expected. But if I look now at the excitations energy for where the excitations these E2 excitations where you see the peaks, they are exactly at the Mott region. So these peaks are coming from the Mott regions, and then for the positive energies you don't see it because to make it doubly occupied you have to pay a lot of price to generate an excitation on the Mott region. So finally, what we can also do, we can study how disorder affects this kind of stripes that we got. Can it generate a lower wavelength for this? So for that, what I will not go through the detail because I think I'm out of time. So what we see, we put an uniform disorder strength here, and this is the solution where the wavelength is 1/4, and then we put a disorder strength of 0.25. And what we see, like the nearest neighboring stripes, they coalesce to form a larger Mott regions, and this kills basically the charge ordering pattern that you are seeing here. But however, for a larger stripe, let's say of the wavelength of 8, this remains relatively stable. But the mechanism of the destruction with disorder is like by the formation of nearest neighbor, kind of formation of a region of Mott which tries to bridge with each other. So finally, I will conclude by saying like what we get from this kind of new formalism is the formation of modulated half-field Mott regions, and that brings a kind of charge density wave with a Mott stripe, if you like that. So what we can stabilize different wave vectors of charge modulation for the same parameter. However, it seems like the regions which have the largest Mott regions, the solutions which have the largest Mott regions are the most stable solutions of each parameter that we have studied. What we see is also like this Mott regions goes away with doping. That is this specially modulated Mott regions that we find, like the stripes we find, they go away with doping. Finally, with disorder, this creates a larger Mott region by merging nearest neighboring stripes. And with that, I will thank you for your attention.
Thank you for the nice talk. Do we have any questions?
But you did not include spin, if I understand well.
Spin?
The spin, so you'd have no modulate, you only have the charge. You
Yes.
not put the spin. So can you generalize this for the spin?
Yes.
Is that done, or did you?
No, I
miss
have
it?
not done it actually, but it should be done. But so basically you have to write like, so then the two, I mean, the bases will not block diagonalize here. We assume like the up and down don't talk with each other.
Right.
We have to calculate everything. The issue is like the analytics becomes tougher and tougher one. So this kind of calculation of these commutators becomes tougher and tougher as you increase the bases. So this is done through Mathematica, but yeah, and once you increase the expressions.
Because the result should be pretty dependent on the spin, no?
Yeah,
Because there's a pi shift between the stripes. I mean,
sure.
Yeah.
But what I can say, like I expect if I do spin, I should form antiferromagnetism in the half-field region. The energetics will change. I mean, I can understand, but yeah, maybe the physics will also a bit. I mean, it's not very well clear. Like, so from here, what we can say, if the speed is not playing a role, it will form a Mott regions.
You have any more questions? Maybe from the online audience, they can speak up. Yeah, if not, I have a question. I don't think I fully understood how you set these phases to be this Qn.
Okay. So what you have to do is, like, let's say this is my self-consistent calculation. So I have an n of I. So this is unknown from beginning. This will come from the calculation. But initially I have to start with a guess for an n of I. So there I can do it as some average number times plus some cosine Qn.
Okay.
And then that Qn might or might not stabilize. After the self-consistent calculation, it might go uniform. But these are all what stabilized. I mean, this is the stabilized solution which you get after self-consistency.
Thank you.
There is another question.
Could you maybe go back to the several solutions where we already had the discussion about the beginning? Or
In the beginning? Okay. Sorry.
yeah, could you maybe explain again figure B, because now I also am confused. So what is the difference? So what do you vary between those?
So this So this is not my calculation, first of all. This is a calculation I have taken from the literature. This is the paper.
Yeah, sorry.
So what they do is they do different calculation like DMRG. Let's say they do DMRG, first of all. So what they do is they change, for like me, like the initial guess of the wave function, I think, and they get different stabilized solutions for different guess that they are doing. So here the parameters are the same. U is same, N is fixed. So then nothing is changing. But you get different candidate solutions. Whatever should be, so one with the lowest energy state will be the most stable. But this is what they try to do here, I think.
Okay. Yeah, that makes sense. Okay, thanks.
Any more questions? If not, then you can thank the speaker again. And with this, we close this session. So now we have a coffee break.